So now I want to talk about how we detect radiation. Okay, there are two ways to detect radiation. There's the Geiger-Müller, and I'll probably pronounce that wrong, so sorry if I'm offending anyone. The Geiger-Müller tube, and there is also the solid state detector. You only need to know how any one of them operates, so we're going to talk about the Geiger-Müller tube. Okay, so basically the Geiger-Müller tube detects the presence of radioactivity because it detects the ionization that the radioactivity causes. So remember, alpha, beta and gamma can all ionize atoms. In other words, they can take neutral atoms and knock electrons out of those atoms to cause the atoms to become positively charged ions, and also then leaving electrons loose outside. That's what causes danger to our cells if it happens in our cells, and ionizing is not particularly good. But all three forms of radiation can cause ionization. Alpha particles the most ionizing, beta the next most ionizing, and then gamma the least ionizing. So the Geiger-Müller basically monitors the amount of ionizing that occurs as a result of the radiation. How does it do that? Well, basically, first of all, it's like a tube, and in here we have a thin mica window. Okay. Now, inside that we have an anode. This is our anode, so this is connected to a positive, a high, large positive power supply connection. So it's connected, so there's a power supply. This is connected to the positive of the power supply, and the negative of the power supply is connected to the outer casing. Okay, or zero, in other words. The radiation passes through the thin mica window, and in here we also have argon atoms that are at a low pressure. Okay, so there's neutral argon atoms in here. When the radiation passes up here, it ionizes an atom or two. So it knocks an electron out. The electron is negative, and it causes one of the atoms to become positively charged. Okay, so it may create more than one ion. But if it creates an ion and an electron, in other words, it ionizes a neutral atom, the electron will then be attracted towards the positive anode. Now, the ion will actually be attracted towards the casing. The electron will move very quickly because there will be a large potential difference between the anode and the casing. So the speed at which the electron moves will result in the fact that the electron itself can then knock an electron out of another atom. So the electron itself can ionize another atom or several atoms. And then when the electron ionizes another atom, that creates an electron which also accelerates towards the anode, and that can cause ionization. So you get a kind of an avalanche of electrons reaching the anode. And obviously, because there's an avalanche, or there's a number of electrons reaching this, the electrons will travel around the circuit. Obviously, there's a power supply effectively here. The electrons will travel around the circuit as a current. A current will flow. Okay, and a current, the detection of a current is the detection of radiation. Now, the current occurs in pulses. As radiation comes up here, an alpha particle will cause this avalanche effect, which in turn creates a kind of a pulse of current going around the circuit. So you can count the number of pulses if you include in here, I'm not going to draw the battery now, if you include in here basically a circuit. Now you don't need to know very much, but it's probably better done in the diagram. A circuit in here, you include an amplifier and a counter. Okay, so have a look at your book because I'm after kind of drawing myself into a hole up here. But basically an amplifier and a counter in here will allow you to count the number of pulses, which then gives you an idea of the number of atoms decaying per second, because you are getting the number of alpha particles or beta particles or whatever per second. That'll relate to the number of pulses that you get, because effectively each alpha particle will result in a kind of a pulse of electrons because it ionizes one atom, but that creates an electron and an ion, a positive ion. The electron is then accelerated due to the high voltage between the anode and the cathode. The electron is accelerated towards the anode. On its way, it ionizes further atoms, and then they create electrons, which will also accelerate towards the anode and may also cause ionization. So you get a pulse for every form of radiation that enters the tube. Okay, is there anything I left out? I don't think so. Argon gas at low pressure, I haven't got them written in, but argon gas, low pressure. Okay, now we need to talk about artificial radioactivity. Okay, so artificial radioactivity, I didn't mention, did I mention the solid state detector is the other type of detector for radiation, but you only need to know one. Okay, the artificial radioactivity, well basically a lot of the stable atoms can be made radioactive. If you take the nucleus of a stable atom and you fire neutrons into it, so you're giving it added neutrons into its nucleus, remember you start to make the nucleus unstable. Okay, the nucleus is already trying to keep those protons together by the strong force. So you pumping neutrons into the mix makes the nucleus unstable. Okay, you've bombarded them with neutrons. The neutrons get captured by the nucleus, it becomes unstable. Okay, and then that is mostly done in nuclear reactors. Okay, and the reason that it's done mostly is to create these unstable nuclei that can be used in medicine and in industry, and I'll explain where they're used in a minute. Okay, but basically most of the radioactive isotopes that are used in medicine are created artificially by bombarding the nucleus of a stable atom with neutrons, making that nucleus unstable. Okay. Now, what are the uses? What are the uses of radioactive elements? Basically, you have, the list is here in your book anyway, so I'm just going to read them out and explain them. Medical imaging, okay, where you can put short-lived isotopes into a particular organ of your body, and then you can see an image of the organ based on the radiation that's given off from those radioactive isotopes. You can use radiation, because radiation affects cancer cells more than it affects good cells. So if you fire radiation at an area that has cancer cells, the cancer cells will be affected much worse than the good cells around it, and you're basically destroying cancerous cells. You can use gamma rays to sterilize food and kill any bacteria in the food. You can use radioisotopes in medicine and in agriculture. You can follow them so that you can trace the movement of certain substances in living matter. Okay, because of the radiation they give off, they can be detected. Carbon dating is a well-known one, where you know basically the age of archaeological specimens can be determined by looking at the activity of the carbon-14. And remember, the carbon-14 the activity depends on the number of undecayed atoms. Okay, and if you know the half-life of something and you can look at its activity, you can predict how old it is. I might do a question separately on that. In industry, you can also use them to check how thick structures are, because if you fire radioactivity then at something, then you can basically detect whether or not it penetrates the thing that you're firing it at, and you will know based on whether it penetrates how thick the object is. A bit like X-rays in some ways. You also have smoke detectors. That's probably one of the most important ones. Americium is the alpha particle. It's the isotope that releases alpha particles and is used in smoke detectors. So basically, in an ionization smoke detector, you've got a radioactive source, and the radioactive source is always emitting alpha particles. Now remember, they work over a short range, so it's not dangerous. And they ionize the air around them, causing electrons and positive ions. Those electrons, a small voltage is applied, and those electrons will form a current. So if you apply a positive and a negative to two sides, the electrons will flow towards the positive. So you will get a current flowing in the circuit. And that's what's the case all the time normally. But when there's a fire or smoke, the smoke will interfere up here. So basically, the smoke tends to stick to the ionized particles. And if the smoke sticks to the ionized particles, then the current will drop because the particles will not flow. So basically, when it drops, your smoke alarm will go off. So it's designed so that when the current drops, the smoke alarm will go off. It triggers the alarm. Okay? And that's basically it.